I will be presenting our work, TreeToaster, that builds an intuition towards IVM optimized compilers. Most database query optimizers represent queries as abstract syntax trees. Here we have query 1 of TPCH on the left, and on the right is Spark's internal representation of the query. Ignore the details because all we care about is that this is a tree of relational operators in the query. And it is this tree that gets fed into the optimizer. Optimizers then specify optimizations over such ASTs as pattern match rules. For example, the selection pushdown rule looks for filter nodes that sit over projections. The optimizer then searches for the occurrence of this pattern in the AST and replaces the match nodes with the filter pushed below the project node. The only problem is that the process of searching for pattern matches is slow. This graph represents the time spent in Spark's optimizer benchmarked on TPCH. This tiny sliver of the total optimization time is what is actually spent doing useful work, which is rewrites to the nodes in the AST. But majority of its time goes towards searching for useful work to do. So why does it spend so much time searching for work? Let's break that down. The optimizer spends 33 to 45% of its total time searching for the patterns to rewrite. Spark's optimizer needs to walk over the AST to look for candidate patterns to rewrite. For example, to look for opportunities to do a selection pushdown, the optimizer starts walking over the AST looking at each node. When it finds the first occurrence of the pattern, it rewrites the AST. But that's not the only occurrence of this pattern in the tree. And when the optimizer needs to replace all the pattern matches, it needs to rework the tree multiple times until it's found all its candidates. The next place where the optimizer spends its time is doing successful pattern matches that leave the tree unchanged. Ineffective pattern matches are a result when the optimizer looks for a pattern and imposes constraints on the pattern. For example, the selection pushdown looks for this pattern, but rewrites the nodes only if the projection is deterministic. Else, it leaves the nodes unchanged. Lastly, the optimizer spends a good fraction of its time repeatedly asking the question, are we done applying all the rules yet? Spark is an extreme case, but similar processing happens in other optimizers too, like Greenplum's Orca, that ends up spending 5 to 20% of its time in searching for patterns to rewrite. So the question is, can we optimize AST-based optimizers? Let's recap. The optimizer defines a set of optimization rules as pattern matches and repeatedly looks for these patterns in the AST. In other terms, we have the full data set. And if we wanted to find specific items in the data set, we have to repeatedly scan over the entire data to answer questions about it. What if we were able to pre-compute everything upfront? Do one full scan over the AST and pre-compute all the nodes that match the patterns the optimizer will ever look for. So the pre-computed tables can speed up the search for pattern matches. But is that all what optimizers do? Optimizers not only spend time looking for pattern matches, but replace a matched pattern with a new set of nodes. So when the nodes change, how do we know which of those tables to update? The pre-computed tables are only good until the nodes in the AST change. What if we went for something a bit simpler? Instead of recording tables over subtrees, let's build tables over the individual nodes in the AST. And since we know exactly which nodes got removed and added after the pattern replacement, this approach would allow us to easily propagate the changes into the tables. So the intuition is to make tables over the nodes in the AST and at the same time be able to maintain these tables as the AST changes over time. Well, that now sounds like something many of us have heard before, right? Incremental view maintenance. But some of you might be wondering, how did a rewrite problem turn into a view maintenance problem? Let's revisit our example. Selection pushdown looks for filters over projections, which is nothing but an equijoin between the filter and the project tables. And the optimizations we discussed amount to materializing the join result. So when the underlying AST changes, the question is, how do we maintain the tables? If we were to design a system that works with IVM, what would it look like? 1, it needs to be able to create views over the data. 2, it needs to understand how to maintain the views as the data changes. And 3, the system needs to be able to produce code that implements IVM, which can maybe be embedded into a compiler. Well, there's a system that does exactly that, TreeToaster. TreeToaster can be compiled to produce code that implements recursive IVM for SQL queries. TreeToaster allows the user to specify the nodes and the changes to the nodes as insert and delete operations over the data. TreeToaster can incrementally maintain its internal state that has information about all the nodes. Additionally, TreeToaster also maintains tables that record information about how nodes in an AST are related. This system meets our needs. So let's take a glance at how it performs. We measure the performance in terms of latency and memory consumption for TreeToaster on large ASTs. This graph shows the comparison between TreeToaster and tree traversals. As expected, TreeToaster has significantly better latency than traversals over the AST. But TreeToaster also ends up consuming twice the amount of memory. Point to note is that TreeToaster is a generalized IVM system for SQL queries, and it makes some assumptions about the data fed into it. Let's talk about where TreeToaster consumes memory. TreeToaster materializes every intermediate query result, and it does so because TreeToaster assumes that these results cannot be quickly reconstructed from the data itself. The second place where TreeToaster consumes memory is its internal state. It maintains tables that encode node relations. The reason it does so is because TreeToaster does not know where its data came from, and it assumes that the underlying data is not queryable. But these assumptions don't hold on ASTs. TreeToaster does not need to materialize all intermediate join results because ASTs encode these join queries within their structure, eliminating the need to materialize all intermediate results. The second question is, why the shadow copy? Contrary to what TreeToaster assumes, the data we feed it is in fact queryable. Nodes in an AST have a sense of who its children are. The only challenge is that the node does not know who its parent is. This problem is not so tricky to solve and can be done by extending the definition of AST nodes to include the parent references, making ASTs fully queryable and eliminating the need for a shadow copy of the AST. A third observation with TreeToaster is with respect to how it updates views when the nodes are rewritten. So let's build to the intuition with an example. Let's consider two rewrites, selection pushdown and collapse project, and the AST as before. When selection pushdown gets applied to the AST, filter node 1 and project node 1 get removed from the AST, and project node 2 and filter node 2 get inserted. Looking at the AST, we know that the rewrite did not create a new opportunity for a collapse project, as project node 2 does not fit the pattern. When the nodes got changed in the AST, TreeToaster propagates these changes to all the base tables and intermediate query results. TreeToaster will recompute the join query over project node 2, even though the node cannot produce a result. So the intuition for TreeToaster is to determine at runtime if an inserted node qualifies for a pattern match. Project 2 will be checked at runtime to see if it matches the pattern for a collapse project. The check is unsuccessful and the node would not be added to the view. Similar runtime checks can be performed for all nodes that change in the AST. To sum up, we built 3 observations into TreeToaster. TreeToaster only maintains views over subtrees in the AST that participate in pattern matches. The addition of the parent pointers to nodes makes it feasible for TreeToaster to drop the shadow copy, cutting the amount of space used. TreeToaster also then implements an optimization that avoids updating views with nodes that will never qualify for pattern matches. To test for performance, we needed a system where we could compile in TreeToaster IVM without significant re-engineering efforts. Just-in-time data is an adaptive data structure that naturally works with large ASTs. Adaptivity in JITs is dictated by a JIT compiler that specifies pattern match rules over the AST generated. The mechanism behind TreeToaster IVM is built into the JIT compiler. We use the YCSP workloads A through F to generate the data and the operations that create the AST. We analyze the performance by comparing 3 mechanisms over the AST. First is the tree traversal, and then the 2 IVM mechanisms we discussed, DBToaster and TreeToaster. The figure shown here is a maintenance latency counted in CPU ticks versus memory consumption counted in pages between doing a tree traversal, DBToaster, and TreeToaster. In terms of latency, for maintaining the different IVM systems, DBToaster performs slightly better than TreeToaster. But in terms of memory consumption, as you can see, DBToaster shows significantly greater memory consumption when compared to TreeToaster. So to bring it all together, TreeToaster consumes no additional memory while keeping up with the latency of DBToaster. Here's a link to our repository where TreeToaster lives. And our paper gives you a more detailed picture of the intuition I described. If you have further questions, please reach out to us via email. Thank you.